Today we're going to talk about a technique for finding the derivative of any relationship between variables, not necessarily functions that are written as y equals something in terms of x. And so we're going to be able to take derivatives of things that are not functions using this method called implicit differentiation. And so the first thing that we're going to do when we do implicit differentiation for some equation like this one here, y squared equals x, where it's not explicitly solved as y equals a function of x. We're going to differentiate both sides of that equation with respect to x, right? Just like we can add or subtract the same number to both sides of an equation, we can differentiate both sides of an equation with respect to x as well. When we do that, we're going to end up with some terms inside that are dy dx terms. If there's more than one of those dy dx terms, we're going to collect them all on one side, and then we'll factor out that dy dx on that side, and then divide by everything else on that side to solve for dy dx. Okay. So let's see why we get this dy dx term. Because if we're going to try to take the derivative of y squared on the left-hand side here, and we're taking the derivative of y squared. Well, that's like saying, let's let u equal y squared, and we're looking for du dx. Well, du dx should be, in this case, if we were using the chain rule here where u is equal to y squared, it would be du dy times dy dx. And so effectively what we're going to do is we're just going to take the derivative of the y term with respect to y, and then we'll multiply that result by dy dx. So every time we take a derivative of a y term, we'll take its derivative normally and multiply the result by dy dx. And this will be the common practice that we'll use for any derivatives that we're taking with respect to a specific variable when the function is written in terms of another variable. So the derivative with respect to x of y squared ought to be the derivative with respect to y of y squared, which is 2y, and then we'll multiply by that dy dx term. And on the right-hand side, the derivative of x with respect to x is just 1. So dividing by 2y gives us that dy dx is equal to 1 over 2y. And it's perfectly acceptable for us to leave this derivative in terms of y, since our original equation had both x's and y's in it. It wasn't just y written as a function of x. And so this tells us that for this particular equation, we can find the slope of the tangent line as long as we know any given y value for this. So we'll do a few more of these. This next one here is dy dx equals y squared minus y. Sorry, we're looking for dy dx when we have y squared minus y is equal to x minus y over x plus 1. So this is the graph of this equation. And what we'll do is we'll just take the derivative of both sides with respect to x. So on the left-hand side, we should get 2y minus 1, all being multiplied by dy dx. And because the derivative of y squared minus y with respect to y is 2y minus 1, and because we are actually trying to take that derivative with respect to x, we have to multiply it by dy dx. And on the right-hand side, that's just a quotient rule problem to take the derivative of that. It should be x plus 1 times the derivative of x minus 1, which is just 1, minus x minus 1 times the derivative of x plus 1, which is just 1, all over x plus 1 squared. So if we simplify the numerator over there, we'll end up with x plus 1 minus x minus 1. So the x minus the x cancels, and we have 1 minus a negative 1, which will give us 2, over x plus 1 squared. And then we're also going to divide by that 2y minus 1. And so we can see that our derivative here now has both x and y terms in it. And in order for us to find the slope at any given point, we need to know both the x and the y coordinates of that point. As we can see, there's lots of there are lots of places on here where, let's say, the x value of 2 has 2 different y values. So we don't know which slope we're talking about unless we have both the x and the y coordinate there to find that slope. Here we have x equals the tangent of y. So if I were to take the derivative with respect to x of x on the left, and the derivative with respect to x of tangent y on the right, that would give us y equals, the derivative of tangent is secant squared, so secant squared y, and then times dy dx. Or dy dx is just equal to 1 over secant squared y, which is perfectly acceptable, or cosine squared y is good as well. Here we've got x cubed plus y cubed minus 9xy equals 0. So on the left-hand side, we actually have all of our variable expressions, and on the right-hand side, it's just 0. So we know that when we take this derivative, the left-hand portion is going to give us a 3x squared for the x cubed. And the y cubed will also give us a 3y squared, but this time it gets multiplied by dy dx because we're finding that derivative with respect to x. And then we have to take the derivative of minus 9xy. Minus 9xy is going to require us to use the product rule because it has an x times a y, 2 different variables being multiplied together against each other. So let's treat minus 9x as our u, and let's treat y as our v, and use the product rule. So the product rule says it should be u times the derivative of v. So that'll be minus 9x. And the derivative of y with respect to x is 1 times dy dx. Then we'll take the derivative of u, so minus 9, and then we'll multiply that by v, which is just 1. So we end up with minus 9x dy dx minus 9y. And on the right-hand side, it just equals 0 because the derivative of 0 is 0. We'll leave our 2 terms that have dy dx on the left-hand side. And in fact, while we leave them there, we'll factor the dy dx out of them, giving us 3y squared minus 9x times dy dx. And we'll add the 9y over to the other side and subtract the 3x. And now we can just divide to get dy dx is 9y minus 3x squared over 3y squared minus 9x. Or if you wish, you can divide everything by 3 to get 3y minus x squared over y squared minus 3x. For this one, we've got x squared y plus xy squared equals 6. And so we're going to actually have to apply the product rule twice on the left side here. Once for x squared y and once for xy squared. So for x squared y, we've got x squared as u, and we've got y as our v. So here's our u and our v. So we'll do u times the derivative of y with respect to x plus the derivative of u, 2x, times y. So that'll start us off there. And now we'll treat this like a u and a v for our product rule. So we'll have plus u, which is x, times the derivative of v, which is 2y times dy dx. And we'll add to that the derivative of x, which is 1, times y squared. And it all equals 0. And be careful not to keep that 6 there. Remember, we're taking the derivative of both sides here. So it ends up equaling 0. And we'll leave our dy dx terms on the left side and factor out the dy dx. And we'll bring the other terms, the y squared comes to the right-hand side of the negative y squared, and the 2xy is a minus 2xy. And then when we divide, we'll end up with dy dx equals negative y squared minus 2xy all over x squared plus 2xy. To find the slope of the circle at 3, -4, we'll just need to use implicit differentiation. So we'll take the derivative of x squared with respect to x and the derivative of y squared with respect to x, meaning that we take the derivative of the y squared with respect to y and then multiply it by dy dx. And we take the derivative of the constant 25 to get 0. So we have 2y dy dx is equal to negative 2x, or dy dx is equal to negative 2x over 2y, or just negative x over y. And we wanted to evaluate this at the point 3, -4. So we'll just plug that in here. We've got negative 3 over -4 should just give us a slope of that circle at that point 3, -4 of 3/4. Now we're being asked to show that the slope is defined at every point on the graph of 2y equals x squared plus sine y. So we'll take a derivative using implicit differentiation to get 2 dy dx equals 2x plus cosine y dy dx. The 2 dy dx is the derivative of 2y with respect to y multiplied by dy dx. The 2x is, of course, the derivative of x squared with respect to x, and the cosine y, that's the derivative of sine y with respect to y, times dy dx. We'll leave the 2x on the right-hand side, but we'll subtract the cosine y dy dx onto the left-hand side so that we can factor out the dy dx to solve for it, giving us dy dx is equal to 2x over 2 minus cosine y. And it says to show that this slope is defined at every point. Well, we know that the cosine of y is defined for every value of y, but we do know that the denominator of a fraction, in this case 2 minus cosine y, can't equal 0. Right? Those would be restrictions on the domain of this. So that would tell us that cosine y is not able to equal 2. Well, the good news is cosine y never equals 2, because the range of cosine is -1 to 1. So we'll never get an output from the cosine function of 2. Therefore, this thing is never undefined. Let's see if we can find the slope of the tangent line to this figure 8 curve here at the point 2√5 over 3, comma 2. So we'll first take a derivative implicitly. 4y cubed dy dx equals 18y dy dx minus 18x. And so, again, we've got the dy dx terms attached to all the y's once we've taken their derivatives. And then we'll bring this 18y over to the left-hand side. And that'll give us 4y cubed dy dx minus 18y dy dx equals -18x. we can factor out the dy dx. And we can divide to get dy dx is equal to negative 18x over 4y cubed minus 18y. Or if we wish to divide everything by 2, that'd be negative 9x over 2y cubed minus 9y. And we want to evaluate this at the point 2 root 5 over 3, comma 2. So in the numerator, we're going to get negative 18 root 5 over 3 when we multiply that 2 root 5 over 3 by negative 9. And in the denominator, we're going to have 2 times 2 cubed minus 9 times 2. And so in the numerator, it looks like we end up with a negative 6 root 5. And in the denominator, it looks like that gives us 16 minus 18, which is negative 2, or we just end up with 3 root 5. Here's a small piece of info that we're going to need for this one is about the word orthogonal. Two curves are said to be orthogonal at a point if they share that point, and if the tangent lines of each of the functions at that shared point happen to be perpendicular to each other. And this isn't a term you're going to need to know for the AP test, or really for my test either, but it's just going to give us a chance to practice a little bit of implicit differentiation. So we want to determine if the following curves, 2x squared plus 3y squared equals 5 and y squared equals x cubed, are orthogonal at 1, 1 and 1, negative 1. So first we need to confirm that both points satisfy both of these equations. So if I plug in 1 here, I get, we'll say at 1, 1, we get 2 plus 3 equals 5. So that works. And at the point 1, negative 1, we get 2 plus 3 equals 5. So that checks out also. And at 1, 1, here we get 1 equals 1. And we also get, at the point 1, negative 1, we still get 1 equals 1. So both points satisfy both of these equations. Therefore, it's possible that the equations are orthogonal to each other at those 2 points. So let's find the slopes of the function at those points. Let's find their tangent line slope. So we'll get a derivative here of 4x and then plus 6y dy dx equal to 0. And for the other one, we'll get 2y dy dx is equal to 3x squared. This will give us dy dx is equal to negative 4x when we subtract the 4x over, and then divide by 6y, or negative 2x over 3y. And on this side, we'll get dy dx is equal to 3x squared over 2y. So in order to determine if the curves are orthogonal at 1, 1, let's plug in that point. So negative 2x over 3y evaluated at 1, 1 is negative 2/3. And 3x squared over 2y evaluated at 1, 1 is equal to positive 3 over 2. And since the slopes here, negative 2/3 and positive 3/2 are opposite reciprocals of each other, that means yes, they are orthogonal at 1, 1, because opposite reciprocal slopes means perpendicular lines. And if we do this at the point 1, negative 1, we have negative 2x over 3y at 1, negative 1. Well, if x is 1, that's negative 2. And if y is one that's -3 or just 2/3, and if we evaluate 3x squared over 2y at 1, -1, we end up with 3 over -2. And those are also opposite reciprocals. And therefore, yes, the curves are both orthogonal to each other at each of those points. So we're going to add one little piece to this now. This notation we've seen fairly recently here. This means the second derivative of this equation with respect to x. So in order to do that, the first thing we can do is find a derivative. 2x plus 2y dy dx, because we're doing this with respect to x, is equal to the derivative of y with respect to x minus 1. And we'll solve this for dy dx. So let's add the 1 to this side, just to keep that positive. And then we'll have dy dx minus 2y dy dx, which will factor that dy dx out, leaving us with 1 minus 2y there. So really, effectively, we've got 2x plus 1 is equal to dy dx times 1 minus 2y. So that will give us the result that dy dx is equal to that 2x plus 1 divided by 1 minus 2y. Well, the way we find a second derivative is by taking the derivative of the derivative. So we need to take the derivative with respect to x of dy dx. Well, in order to do that, we have to treat this as a quotient of two functions, u divided by v. So this will start out as v, right? The second derivative is v, or 1 minus 2y, times the derivative of u, so v du, minus u times the derivative of v. And we have to be careful here. As we take the derivative of v, the 1 goes away. And the derivative of -2y is -2. But remember that we're making or taking a derivative with respect to x. So the derivative of -2y with respect to x is -2 times dy dx. And this is all over the denominator, 1 minus 2y squared. Now, this answer isn't complete yet because we have this little term in here, this dy dx term in here that we need to get rid of. Well, the way we're going to get rid of that is I'm going to first put this minus sign here and this minus sign here together as a plus. We're going to have plus that 2 times the 2x plus 1, and then times dy dx. Well, all we have to do is replace the dy dx with dy dx, the thing we found earlier, 2x plus 1 over 1 minus 2y. And it's still all divided by 1 minus 2y squared. And this is a perfectly acceptable answer. It's possible to simplify that down so that it's not a complex fraction, right? You just distribute everything over here together, and then you would multiply everything on this side by 1 minus 2y for 1 minus 2y to get a common denominator and bring them all together. But this answer right here is perfectly good. So we'll do one more of these, and then we're going to be done talking about implicit differentiation. So to take the derivative of xy, we need the product rule, x times the derivative of y with respect to x, plus y times the derivative of x, which is just 1. And then the minus y squared becomes minus 2y dy dx. The minus x becomes minus 1, and the 0, its derivative is still just 0. So we'll bring the 1 over to the other side, and the y over as a minus y. And then we'll factor the dy dx out of these two terms. And we'll divide to get dy dx is equal to 1 minus y over x minus 2y. And from there, we'll actually go to a second page here, just so we have a little more room this time. If dy dx is 1 minus y over x minus 2y, then our second derivative needs to be found using the quotient rule. It should be the denominator times the derivative of the numerator, which is negative dy dx. So v du minus u dv. And dv is 1 minus 2 dy dx. And the derivative of x is 1, and the derivative of minus 2y is minus 2 dy dx. All over x minus 2y squared. And now we just have to go back in, and we will write x minus 2y here, and we'll have our negative 1 minus y over x minus 2y, because that's dy dx, minus 1 minus y times 1 minus 2 times our dy dx, 1 minus y over x minus 2y, all over x minus 2y squared. And if we look at that, there's a couple things we could do here if we wanted to. We could just drop the x minus 2y that's over here, and we cancel it with this one if we wanted to simplify that down a bit. And then we could distribute that 2 over here out into the numerator. And if we really wanted to, we could get a common denominator of x minus 2y throughout everything and simplify it down further, but I'm perfectly good with this as a final answer. It might be nice to cancel those out, but again, not the end of the world if we don't do that here. The main idea is just to know how to get that second derivative input. So that's going to be it for what we're going to talk about implicit differentiation. We're going to use this for some stuff in applications of the derivative called related rates. And we've only got a few more different rules for derivatives that we need to prove, and then we'll be done with this unit. So we'll take a look at a couple of those next time, but that's it for today.